Welcome back to part two of the discussion on chemical equilibrium. A sequence of videos to follow on this particular part two will be on Le Chatelier's principle. Now, in lieu of the time that we have left in the course, I may not go in depth on every one of these concepts. So I have left some tips on each one of the topic as a form of cutting things short. Now, if we had the luxury of having another month, then I probably would go into greater details on it. However, like I said when I first started this topic, what we're about to talk about was exactly on my doctoral dissertation work. So since I have researched the topic, I want to make sure that I give you the information in the correct way. I've spent most 3.5 years working on trying to present this topic in the correct light. So I will try to give you that information. All I will not do is go into greater detail because we just don't have the luxury of time. All right, so without further delay, let's redefine chemical equilibrium. I have defined it for you in the previous video. When the rate of forward and reverse reactions are equal. Don't forget, it is the rates, not concentration. If you plan to sit for a standardized exam like MCAT, DAT, any of those, you would see what's the definition of a dynamic chemical equilibrium, and it means the forward and reverse reaction rates are equal. Please do not get this question wrong because it's as simple as it gets, right? All right, now let's go into the actual Le Chatelier's principle. What it is, if you remember, I've emphasized chemical equilibrium involves a reaction with a double-headed arrow. That is, A, if A is a reactant, it can go to make B, and when a certain amount of B is made, it reverses back to produce more A, right? So this is same as this. So if you write it this way, or this way, they both mean the same, okay? So if what this statement is really trying to say is, if you make a change in one side of the reaction, okay, the system would adjust itself, okay, to reestablish equilibrium. Okay, now this statement is more technical, and that was one of the things, is how do we define it in a way that it makes more sense. Now, when you write this way, okay, or this way, what we're really implying is the system is at equilibrium. What this principle says is, say a system is at equilibrium and you disturb it, the system would try to force itself to make changes to reestablish equilibrium. The word reestablish is often missed out when people teach this concept, and that leads to a lot of problem. You might think really just a word, you bet it is. So a system would try to reestablish equilibrium, and that's kind of part of what this principle is saying. Don't worry, I don't think I'm going to test you what Le Chatelier's principle itself is, but there are 4 different ways you can disturb a system. Those are, you can change the concentration of either the reactants or the products at any point of time during equilibrium is established, and you can encounter some changes because of that. You can change temperature of the reaction itself, and you can change pressure. Now, I am only going to talk volume from the pressure perspective. I am not actually going to go into effect of volume because that's one of the misconceptions that's being reinforced by wrong instructions. So given where you will encounter it, I'm just going to say that there's not a high chance that you will encounter it. So I'm just not going to teach that because, it's just a little bit too complicated and it's not quite straightforward. All right. And the 4th thing is addition of catalyst. So let's understand one thing one more time. You have a reaction that's already attained chemical equilibrium, and you can disturb it using any one of these 4 methods. The system would try to adjust itself in one of the many ways. That's why I'm saying one of the many ways to reestablish equilibrium. All right, and these are the four methods, and I'm going to try to explain concentration in this video, and then try to do temperature, pressure, and catalyst as separate videos on their own. Okay. All right, so change of concentration. For instance, I have this reaction, and you always want to write the Kc expression, and I did. So this is the Kc expression for this equation, right? All right, so let's say I had some N2. The system is already at equilibrium, right? So what happens when I add N2? Okay, I have disturbed this side of the equation. So the system would adjust itself so that to reestablish equilibrium. Think of it this way. When you add more N2, the denominator is higher now, right, compared to the numerator. So the numerator has to come up to counterbalance this increase. And the only way it can do it is the denominator has to go down. So initially you will see a sudden influx of the denominator, right? And then what happens is the numerator starts to increase and the denominator starts to decrease a little bit. So this is the numerator, this is the denominator. And then the system would eventually come back to a new equilibrium, okay? You will not have the same amounts that you started, but the Kc value will be the same. Say the new equilibrium is called Kc1. Kc will be equal to Kc1. That doesn't mean each one of these values would also be equal. Does that make sense? Okay. So in a nutshell, if you add N2, okay, when equilibrium is reestablished, okay, you will have less N2, less H2. I'm using the word less, and then I'm adding more NH3. Okay. Because we made the change on this side by adding N2, N2 is on this side. So essentially we've added more of a reactant. So the side you make the change tends to have less effect, tend to have the most effect. That means if you add something to the reactant side, when the equilibrium is reestablished, you will tend to have less N2, less H2, because they're both on the reactant side. It affects the other reactant too. Even though you only added N2, you'll have less H2 and you'll have more NH3. Remember I said, initially there's a sudden increase of the denominator as a whole because you've just added more in the denominator. But we want to go back to the same value for Kc. Okay, imagine a value that's X. You have to go back to the X. The only way that will happen is the denominator has to decrease and the numerator has to increase. That means we will have slightly less reactants compared to what we started with, and then we will have slightly more products than what we started with at the initial equilibrium, right? So more NH3. So say what if we added more NH3? Same deal. When equilibrium is reestablished, we've added now more products, right? So now what happens here is this is the first case for add N2, right? This is for add N2. Okay. So what happens now is now we have a sudden influx of the numerator and we have to decrease this, right? Slowly, so with constant increase of this to reestablish equilibrium, right? Basically, we have to get back to where we started. So what that means is when equilibrium is reestablished, we will have more N2, more H2, and less NH3 compared to what we started at the initial equilibrium. Okay, this is very easy. It's not at all difficult. Okay, whichever side you add, say if you remove N2, then it will have the opposite effect. Okay, if you remove N2, okay, when equilibrium is reestablished, this is where we removed, right? Now we have more of this, right? Think of it this way. You have removed N2. I'm going to draw a line here. If you remove N2, that means now we've taken some weight off the seesaw so that this side has more. So that's essentially same as adding NH3. So now we have more of this. The numerator is more because that's why we write the Kc expression. We've removed this, so the numerator is now all of a sudden big. R is in excess. So what happens now is, again, this has to decrease, this has to increase to get back to the same equilibrium, right? So that means, again, when you remove N2, we'll have more N2 in the end, more H2, and less NH3. I don't know if you want me to go through the other scenario, but I'll do it anyways, so that you have it. Okay. So let's say we remove NH3. Okay. Just think of it as pure math. Okay. So if you remove NH3, you reduce the numerator value, right? So that means now all of a sudden we have more denominator, right? So that means this has to go up now and this has to decrease. So that means we will now have, when equilibrium is reestablished, we will have more NH3, less N2, and H2. That's all. I've given 4 scenarios, right? So here's a tip. Okay, sorry, I shouldn't have done this, but you know what? I can put the tip again. You can see that if you add more reactant, you make more products and lose reactants. It's very important that you remember even equilibrium is reestablished. Okay, that word is rarely used because your system would still be double-headed when equilibrium is reestablished. So what I have drawn here in terms of reaction, I have summarized it here. Now it's important I said the word generally. Means don't think of this some kind of rule, but for the most part in a general chemistry class, this rule would work. At least the test questions will be written revolving around this. Okay, so I can also provide a handout of the tip on a piece of paper in class, but I think you can still read through this. So if you had a reactant, you make more products, lose reactants. And if you lose a reactant, which is you make more reactants and lose more products. I don't want to read through the whole screen, but I recommend you actually understand there's a crisscross pattern. Adding a product or removing a reactant is the same effect as adding a reactant or removing a product. So essentially, if you see these 2 conditions are the same, these 2 conditions are the same. That is, it results in the same net effect when equilibrium is reestablished. All right, so I don't want to dwell more into it. I think I've said what I had to say on this topic. So I'm going to stop the video here, and then when I come back, I'm going to explain the effect of change in temperature, and then change in pressure, and then finally addition of catalyst, right? So stay tuned.